Okay. Thanks everyone for coming. Hopefully you got enough coffee on that last break, or that I won't put you to sleep if you didn't. Yeah, this is Cassandra by example, data modeling with CQL3. If you haven't heard what CQL is, how many people were in Sylvain's talk in the last session? Okay, so there was more overlap than I was expecting when I talked to Sylvain. So hopefully I won't bore you, but there's also some different materials. CQL is a query language for Cassandra. I'm gonna need Sylvain in here? I don't think so. I'm gonna need to talk to him because it's actually, I think, a little bit more SQL than he's giving it credit. We used to call it an alternative query interface, but it is really getting a lot of traction. It seems to be where all the mind share's at. I think it's destined to be the de facto one. I kind of consider it that way. And it's been out for 3 major releases now, which is, in dog years is a long time. Cassandra moves really fast. And I've done entire talks on the justification for why I think this is a good idea. I won't get into that much detail here. I'll just stick with the fact that this is by far the most approachable way to code for Cassandra, to write an application against Cassandra. The old way, the only way at one point, was the thrift RPC. And this is what the code would look like in Java to write a single row with one column in thrift RPC. Now, I know this slide is unreadable, probably even from the front row. Actually, if you're sitting in front of the IDE, it's pretty unreadable. I didn't contrive it to be this verbose. It really is that verbose. And worse. You hear me now? Yeah. All right. Yeah, so I won't go through this, but just suffice it to say, it's pretty bad. It doesn't mentally map well to the way your data is modeled. It's just not a very good way of doing it. By comparison, this would do the exact same thing with CQL. And most people who've gotten to this stage in the game have already done something with SQL at some point in their career, and even if you didn't, it just pretty much reads in English what it's going to be doing. So this is much easier to do. It's much easier for the next person that comes along behind you to reason what's the intent, and it's just the easiest way to do it. So do this, not this. Okay. So before we get started, though, I want to take a little detour into partitioning. It feels like this is the wrong talk to be talking about Cassandra's architecture, but there are aspects of Cassandra's architecture that influence how you have to model your data, and understanding that will I think, make it easier. So for those that sat in Sylvain's talk, I apologize for any repetition here, but Cassandra is a content addressable system, so if you can imagine, the data in Cassandra is stored as rows, and rows are identified by a key, and you can think of the key as the primary key. That is a good analogy. It's the first level of indexing, and you look up rows in Cassandra by that key. So if you can imagine taking a namespace of all the keys in your key space, and mapping them onto a ring or a clock face, in sorted order, ascending, and wrapping around from the highest to the lowest. You could then divide or partition that ring up and give each partition to a node in your cluster. Then it's a simple matter of taking that key and finding where it sorts in that namespace, and taking the closest node to it, working around the ring. So then your row, the row that you must look up by key, is pinned to a machine. Now, there's replication and whatnot, so it's pinned to multiple machines, but where it lives in the cluster, where it's placed, is a function of the data itself. So this is to tell you that your unit of access is the row. A row is what you can query quickly and easily. A row is what you can update atomically, in a performant fashion, isolated. You want your queries, in as much as is possible, you want your queries to be something that can be answered from within a single row. So all this is a fancy way of saying you have to denormalize. You have to denormalize so that you can put more of your data within this unit of access, the row. And that's kind of the reason for the specificity in this talk, that it's a CQL3, because CQL3 comes with some abstractions, some new abstractions that make that much easier. So the way I'm going to do this is we have this application that we've floated around for a while. It's a real app. It's a really simple clone of Twitter, just because Twitter's something everybody understands, and it's easy to think about. I'm not going to step through any code examples per se. I just SQL queries because that's a painful thing to do. But you can download this app. It's a real app. And even if Python's not your thing, all of the stuff that accesses the database is in a top-level file called cast.py, and Python's pretty readable, so you could pick through it pretty easily if you wanted to. It shouldn't be taken verbatim as an example of how anybody thinks that an application should be written for Cassandra or anything, really. It makes some assumptions about, we favor simplicity over correctness, I guess, is the best way to say it. And there's also some obvious mistakes and some obvious things missing because it is used as a tool for learning. So that gives things to talk about and things for people to do with it. If you pulled down Cassandra and you fired up the embedded web server and pointed your browser at the root URL, this is what you'd see, which is pretty much what you'd see if you went to Twitter and you weren't logged in. You see the tweets from everyone, a stream in sorted time-sorted order, descending the newest tweet at the top. You have a way of logging, of creating an account and logging in. It's kind of doubled up on the same form. And once you're logged in, your view of the tweets, the stream, changes to those of the people you follow. And of course, you obviously get a way to tweet yourself. Because you need to follow people to see the tweets of those you follow, there's an interface here that you can find people to follow and follow them. And finally, if you see a user's nick, it's something, it's a hyperlink you can click on, and that will take you to a display of all of their tweets, specifically that person's tweets. Again, sorted temporally, descending. And so these are sort of the functions I'm going to go through, the pages I'm going to go through, how you would build a schema and construct the queries to produce these sorts of results. So we'll start by signing up a user. You've got this form with a username and password field you can enter twice for comparison. We're going to store the username and the password, so we need a table for that. This table has two attributes, one for the username, one for the password. The primary key is the username, so that is our row key, which is appropriate because we're going to want to look up the password for a user. So there'll always be a user where username equals some user predicate. Inserting into that table is just perfectly valid SQL. Should look quite familiar. The semantics of an insert, though, are identical to an update. So this will succeed even if you have an existing user. So obviously, if there was another user called Meg and we didn't check first, we would override it. This statement wouldn't fail if there was an existing user. So you would definitely want to do that. We include both of them because it's really hard to say what the element of least surprise would be if one were missing or if you took something else entirely. But I think it's good, and you can just use it to communicate the intent. So if it's your intent to insert a new row, use insert. If it's your intent to update an existing row, use update, and then that'll kind of make the code a little bit more readable, I think. So now you've got a user. To sign that user in, like I said, all we need to do is select the password from the users table where the username equals Meg, and then we can verify that the password she gave is correct and log her in. So now Meg has an account and she's logged in. She'll need to follow some people. She'll need to add some friends in order to be able to have a timeline populated with the tweets she's interested in. So for this, we'll create a table called following, which has two attributes: the username, which in this case, when we're looking for Meg's list of people she follows, we'll do a query where username equals Meg. So this is our row key, and we have an additional attribute followed, which is whoever it is that she is following. And so this is what's new in CQL3, or this is a new feature, this sort of clustered primary key, this grouping to create the primary key. So the very first element whenever you see this is the row key. Thus our predicate, will have to include a where username equals something. This is where we're going to look up the row. By adding the followed on here, what we're doing is making that a many-to-one relationship, many followed to the one username. Inserting into a row like this would be just like inserting into a table. Wherever username is Meg in this insert statement, under the covers within Cassandra, that's all going to be put into one row. But every time we insert with a different followed attribute, it's going to add that additional followed. And if we query select followed from following where username is Meg, we get back a nice tabular result set that includes all of the users whom Meg follows. So it's kind of like we're encoding a table within the row. And so that's why I say that you must denormalize, but this feature, new in CQL3, new with the release of Cassandra 1.2, goes a long way in making that easier, making that more natural thing to do. So now we have a list of the people whom Meg follows, but for every person Meg follows, we need to know, at some point we're going to need to know the inverse of that. Meg followed Stewie, so at some point we're going to need to know who's following Stewie, and so we need the inverse of that relationship. So for that, we'll create another table, which other than the name of the table and the name of the additional attribute is identical to the first, but this one's meant to track that inverse relationship. So it works the same way. We can do an insert here that says, where username is Stewie, Meg is someone who follows Stewie. And then if we do the query, select followers from following where username equals Stewie, then we get a list of the people who's following Stewie. What this means is that every time someone creates one of these friend relationships, whenever someone follows someone else, we need to insert that into both of those tables so that we have both sides of that picture. And that's the way that's done in Cassandra, is with a batch mutation, the syntax of which looks like this. So every time a following relationship is created, that's what we're going to do. We're going to insert into both tables the one for the person who's following and the followee. But for Meg to see any tweets from the people she's followed, they're going to have to create a tweet first. So if you can imagine, Stewie types in a tweet and mashes post, then we can track through how we store these tweets. And here's where we're going to see much of this denormalization. And if you come from an SQL background, this might be the part where your stomach starts to turn a bit. So just a fair warning. Okay. So the first thing we'll need a sort of discrete tweet store, because people share tweets, and so you need a way of effectively permalinking back to that tweet. So we create a table called tweets, and we'll give it a unique ID for the primary key. That'll be the row key. The lookup key is that ID. UUIDs feature rather prominently in Cassandra because we need something that's globally unique. And something like a monotonically increasing integer would require coordination, and this is a distributed database. So we have a tweet ID, which is a UUID, and we have a username in the body, so that when we query this out, we'll have everything we need. And then obviously inserting into that should again look very familiar. It's just standard SQL. But this table is going to fall far short of all of the things that we need. If you remember, we need a way of producing a page that shows all of the tweets from a user, sorted temporally, descending. We need one that shows the tweets of all of the people we follow, again, time descending. And since we're going to want to page through these, we also need a way of querying by using a time predicate. Where we need to say where date is greater than X and less than Y. So that tweets table is not nearly enough. So let's first look at the simpler one, the tweets for a specific user. So we'll do that by creating a table called userLine with 3 attributes. The username, which you'll see from the primary key definition down here, again, is the row key. So we're going to be looking up this userLine for a user. And we'll give it a tweet ID as well. This one's a time UUID. And then we'll store the body of the tweet as well, so that when we query this out, we've got it all there. So the previous table just used a UUID. This one uses a time UUID, so that begs the question, what is a time UUID, and or why are we using that here? A type 1 UUID or time UUID is a UUID. It's just the first version or first iteration of that standard. And it was kind of abandoned in favor of other forms of UUID because it kind of exposes the machine it was created on and obviously the time it was created on, because the first 60 bits of that UUID are a timestamp. It's kind of a weird timestamp. It's 100 nanosecond units from like a 16th century epoch, but it is a timestamp. And because it's the first 60 bits, they sort temporally. And they have a relatively high resolution. So what that lets us do is we can do a select on this table we've created of the tweet ID in the body. And you'll see in this projection we're applying a date of function on the tweet ID so that the results we get back are actually like a timestamp. We'll have Cassandra extract the date for us or return the date for us instead of the UUID. We select that from the user line where the username is Stewie because we're interested in the list of tweets he's created, and then we can use predicates on the time UUID that are date-based. This min-time UUID function is simply because, like I said, the time UUID has sub-second resolution, and we've given a timestamp that is in seconds. So this just says, pick the floor, the lowest possible time UUID for that timestamp. And finally, we're going to order it by the tweet ID, that time UUID descending, so that we get them in reverse sorted order, and limited to 40 because that's what we show on the page. And the result from a query like that would look something like this, which should be sufficient, at least in the minimal sense, to create that page, the page with all of Stewie's tweets. Okay, so we also need the timeline, which is all of the tweets that a user is interested in, all of the ones from the people he follows or she follows. So for this, we'll create another table that looks almost like the last one, with the exception of this additional attribute called posted by, which is simply because the username in this case is the person who we're going to display these tweets for. And since they're from a variety of different authors, presumably we need a way of identifying the author as well. What we're doing in all of these cases is we're sort of pre-computing a materialized view for the thing we want to look at. And in this case, we're looking at a stream of tweets from a variety of different authors, so we need to add that additional attribute. But it's otherwise identical. So the query to extract the data is also almost identical, with the exception of we're putting this additional attribute in the projection so that we get it out as in the results as well. But that means, much like the following follower table, for every tweet, we're going to have to insert this into multiple tables. We're going to have to insert it into the tweets table so that we can do a discrete lookup based on the tweet ID. Since a time UUID is a UUID, I should point out that where we're creating time UUIDs and using a time UUID type in these userLine and timeline tables, we can also use that same UUID for the tweets table. You would want to do that so that you could link from the timelines back to the discrete one. We would need to store it into that discrete tweets table. We would also need to store it into the user line for that user, the one who was creating it. And then for every follower that user had, remember I said at some point we're going to want to know who's following Stewie. For every user who follows Stewie, we will also need to store it into their timeline, into their materialized view of the tweets they're interested in. And again, this is something you probably want to wrap in a batch mutation so that it's atomic. This is all data that's meant to correspond with each other, so you want it to be consistent. And that is pretty much it. I mean, that's pretty much what I wanted to show. That you need to think of your queries, from reverse. You need to think of what the results you want to get back should look like, and store that as opposed to, the normalized data, the normalized representation of that. I put up here, don't fear duplication because space is the cheapest sort of variable in the scaling equation, which is true, but to be fair, there are many reasons why you don't want to duplicate, and that's probably the least of them. This is something that, this is a trade-off that we're forced to make for this kind of decentralizations distribution. So get used to it if you need this kind of scale. Creating these sorts of one-to-many relationships, within a single row, is going to mean that the number of columns in that row, could become quite large. The row could become quite wide. But that's pretty okay too, because the upper bound on the number of columns you can store in a row is quite high. It's about 2 billion. There may be reasons why you don't want to go quite that high, but of course, you don't want the number of them to grow unbounded, which is, in this naive Cassandra sample application would be a problem. Eventually, somebody would tweet enough, for example, to blow a row. But you can still go quite wide. That's not really a problem. And if you want to play around with the sample app, but you don't like Python and you have Java, I do have a link here to one that's written in Java. And that's pretty much it. So if anyone has questions, I think we probably have more than enough time to take them. I went through it a lot faster than I thought I would.
No? Okay. Thank you to the speaker.
Is that...